So I guess we're ready to go. Thank you, Defan. So this was a diagram I like because it gives you a physical picture of why an oscillating electron, oscillating in and out of the board, is producing X-rays when otherwise we would think it was producing some, it would radiate at a wavelength that was sort of like the, could be identical to the undulated period, several centimeters, but that's not what we see. And this picture gives us a good idea why, because as this electron is oscillating in and out of the board, it's moving forward at really very close to the speed of light. So the wavefronts all pile up, and the distance between wavefronts is very short, and that is what we call the wavelength. So the wavelength on axis is quite short. We don't know how short, but it depends on this relativistic effect. And we observe that there's an off-axis lengthening of the period. So as you go off axis, you get longer wavelengths. So that's one figure I like from what we did. And then this one gives us some real insight as to how short that wavelength should be. We actually derive what's called at the bottom here, this undulator equation. And we're going to derive the middle term today. But basically we said if the electron is going through at a highly relativistic speed, then it, first of all, what it sees then, or feels in the magnetic field, is a Lorentz contracted period. It's like the meter stick. When the observer flies past the meter stick at a very high speed, approaching the speed of light, you see an apparent shortening of the meter stick. The centimeters become much smaller, the intervals. And for us, if you put yourself in the frame of reference, moving with the electron, in that frame of reference, you'll see this same Lorentz contraction, but now it's taking you from an undulated period to an undulated period over gamma. Gamma is a big number. For the ALS, it's like 4,000. For the hard X-ray machines, it's 12,000 or even more. So this is a big reduction. And in that frame of reference, the electron is oscillating, and we know already that when an electron oscillates and there's no relativistic effects in that frame of reference, we get what's called dipole radiation. It's a sine squared behavior, and it's actually a wraparound donut pattern. And so that's in the frame of reference moving with the electron, and the spectral width, I've written it here, inverted, lambda over delta lambda is equal to n, the number of cycles of oscillation. So this thing is oscillating in that frame of reference, appears to be radiating at a wavelength lambda u over gamma with a spectral bandwidth n, or 1 over n, okay? But that's in the frame of reference moving with the electron. Over here, where this radiation is coming towards our sample, the sample sees this radiation, but with a Doppler shift, because this source is moving towards it. And the relativistically correct Doppler shift looks familiar, but it has this gamma in it. And when we put in here, so this is saying that the wavelength seen here, lambda, is this lambda prime from this frame of reference moving at it with this high speed, high velocity. Okay, so when we combine these things and run them together, we get what's very close to being the undulator equation. It has the most important feature, that is that the wavelength on axis is lambda u over 2 gamma squared. So there was a gamma from the Lorentz contraction and a 2 gamma from the Doppler, and this is a really big factor. So our 3 centimeter wavelength, if this was 4,000 at the ALS, so you've got 1.6 times 10 to the 7th times 2, so it's about 3 times 10 to the 7th. This was 3 centimeters, so you've got a nanometer. Is that right? It was a centimeter divided by 10 to the 7th. Yeah, it's a nanometer. So you're getting a nanometer on axis. So that explains why when we look at undulator, or when we go to use undulator radiation, why are we getting X-rays coming out, okay? And we use this relationship also to show, we wrote it twice, once for directly on axis and one for some angle off axis, a small angle. And we combine those equations. We wrote it twice, once with the theta, and we call this lambda plus delta lambda, and one on axis, so this one out, and combined those, and we found that there was a central radiation cone of 1 over gamma square root of n, where n was the number of periods. Excuse me. Okay. And what I told you was that actually this analysis was pretty okay about the Lorentz contraction and the Doppler shift, but it turns out that gamma was the value for the electron just as it was entering the magnet structure. But then in the magnet structure, because of the Lorentz force, and which causes this oscillation of velocity and amplitude, that means that there's energy going into transverse motion. And in general, for electrons or charged particles in a magnetic field, there's no change in energy. There may be a change in vector direction, but the magnitude, the v squared x plus vz squared, is a constant. So we could use that. So we could see that this transverse motion is slowing the electrons down, and it's going to introduce an effective value for gamma. It'll be slower because of the magnetic field. And that's what we're going to do, I think, in the next slide, is we're going to find out, okay, how much does the magnetic field change the value of gamma, the effective gamma? And as you bring these magnet structures from a very open position to a very closed position, this oscillation is going to be same period, but the amplitude is going to be much larger and the velocities are going to be much larger. And so as you close the magnet structure, you're going to be slowing the electrons down more and more because they're spending more and more time moving laterally. And as we'll see in a moment, we'll wind up getting an effective value for gamma, which is somewhat different because of the magnetic field. And when we substitute it here and here, we will just naturally arrive with a magnetic tuning term, okay? So that's what's coming next. Does that provoke any thoughts on anyone? You thinking about that before? Or it's clear enough? Okay. So here's our diagram. And again, actually the only reason I put this up was to remind me to say something about the oscillation here. So this, you could imagine this as two jaws, magnetic jaws, really. Okay, and they're, by the way, several meters long. If this is 3 centimeters and you have, let's say, 70 periods, that's 3 times 70, 210. So you're getting up around 2 meters or something. The ALS has room for almost 5 meters. And sometimes they'll have, so there's some are like n is equal to 55 is one, or 89 is another popular one. With the upgrade, they're going to have one where n is greater than 200 because they're going to be trying to produce very short wavelengths, okay? At any rate, so as you bring these two jaws closer together, it's called, the opening here is called the gap. As you start reducing the gap, the magnetic field on axis becomes stronger, and the electron oscillation, the V cross B term, is it's F equals ma. We wind up with mass times velocity, even though it's relativistic, is V cross B. And so the B is getting stronger. The V cross B is getting stronger, and the oscillations, the transverse oscillations, get larger. And that's where all this comes from. And we're going to see that in a moment. We're actually going to do a calculation of the electron dynamics. So here we go. Here is our diagram. Here's the electrons entering with some value of gamma. They're going along the z-axis through the magnet structure. There's a periodic magnetic field shown here, okay? And the V cross B term is going to cause an oscillation in the x direction, okay? So, so here's our relativistically correct force equation. This would be, normally would be our force is equal to mass times acceleration here, but we don't write it relativistically. We write it in terms of the rate of change of momentum, where the relativistic momentum is gamma times mv. Okay, so we're going to put that in here. Okay, and we're going to notice that there's an applied magnetic field, and in fact, it's an extremely strong magnetic field. It's measured in Tesla, so it's a very strong magnetic field, and V is as big as we can get it. It's almost C. So this is a very strong term, and this is the only electric field around is the electric field in the X-rays we generate, and that's very small. So this equation reduces to this, okay, to an extremely high degree of accuracy. So what we're going to do is say that we're going to play with the velocities that are involved here. And I'm going to say that there is a velocity Vz and there's an induced velocity V sub x. And we would like to use this to calculate the V sub x. So we're going to be interested in the Vz cross B. So for this V, we're going to say it's roughly Vz. This is almost C. This oscillation is not relativistic. It's relatively small. So in this equation, we could, to first order, we can follow this up by doing expansion in orders of decreasing size, but it's reasonable to put this as Vz. This is By, so this is what we have here. And here, this is the rate of change of gamma mv. Well, gamma and m are not changing. In this particular geometry, they're not changing. So this term just becomes m gamma times the rate of change of velocity, in this case in the x direction, because we took a Vz and a By. So this is, which was solving that portion, that scalar portion of a vector equation. So this is our equation, and now we're going to solve for V sub x. We're going to get this V sub x, and with that, we can start to understand what is the change in velocity in the z direction. You know, that Vz, not quite a constant, very high. So let's see how we solve this. This is our equation now, again, to solve for the lateral motion, which is this is the acceleration. The charge is accelerated, it's going to radiate. So this is the term, the acceleration, which is driving the production of X-rays. So this is our equation. We'll write Vz as dz dt, and By will substitute for this form. So we have an amplitude and a sign. So this is the periodic magnetic field. We see in this equation, and this exists only through the length of the undulator, from z equals 0 to the number of periods times the period. That's the length. Okay, so this would be like a few meters. Okay, so we see there's a dt on both sides. We could cancel that, and the remaining part of the equation is what's shown here at the bottom. So this gets repeated at the top of the next slide. Okay, here it is. Okay, so we'd like to integrate both sides. Again, we're trying to solve for V sub x. So we're going to integrate both sides. So the integration cancels the derivative. The integral cancels the derivative. There'll be a constant, of course. And we're left with m gamma times V sub x is equal to the integral of all of this. So the B0 and the E come outside. And in fact, we want to integrate a sign in dz. So we're going to change the dz to d 2 pi z over lambda u, so the arguments match, okay, to do the integration of the sign. So if we put a 2 pi over lambda here, we have to put a lambda u over 2 pi out front. Now we can do the integration. This is just a cosine, okay? Everything else is fixed. So the integral is this. We can divide through by m gamma, and now we have a solution for V sub x, okay? It depends on the cosine. The velocity is out of phase with the sign, okay? And what's left is c over gamma out in front, and all of this stuff with the magnetic field gets thrown into a non-dimensional capital K, sometimes called a deflection parameter, or just sometimes the magnet, the periodic magnet constant, or something like that. Anyway, it's a non-dimensional, and typically, by the way, for undulators, it's going to be of order unity, something like k equals a half to maybe a couple, maybe k equals 2 or 3. If k gets much higher, we'll see that other things start to happen, harmonics. Anyway, so we've started with we wrote the equivalent of F equals ma, and we solve for the oscillation, the transverse oscillation. And we've got it. If we took a derivative, we'd get the acceleration. We know how to calculate that. And this K factor is what's shown here, okay? So for instance, with a half Tesla field and a period of 3 centimeters, the K value would be something like 1.5. So I'm guessing that our magnetic field strengths are less than a half Tesla. Okay, it's more like a third. I don't remember exactly what it was. So, okay, so this is interesting. We found out about the transverse motion, but you know, we said that the total velocity is not changed by the magnetic field, so that the total velocity v squared, which is equal to vz squared plus vx squared, that's a constant. And we've just solved for vx, so we can go back and solve for vz. Okay, so that's what we're going to do on the next slide, I hope. Okay. So yeah, so in a magnetic field, gamma is a constant. Okay, this is how we define gamma. I've substituted v squared as vz squared plus vx squared. There's no motion in the y direction. And I'm going to square both sides and solve for vz. And if I do that, this is what I find. That vz squared over c squared is 1 minus 1 over gamma squared. So this would be extremely small. And this is vx, this is the lateral velocity. This is also small compared to c. So I could, I see I could have one other step to show you here. We can put here for Vx the solution we just found on the previous page, except that it's squared, okay? But in taking the square root to find this, all of these things are small. So we can just have 1 minus a half minus this a half. And so Vz, the axial velocity, is now 1 minus 1 over 2 gamma squared. That's what it would be if there were no magnetic field. So if K was 0, we would see that Vz is this very close to C. In fact, you could use this. Just test yourself. You can do it while I'm talking if you want. How close to, what is Vz over C? How close to unity is it? It's only off by this number. So again, if gamma was, if gamma was 4,000 for the ALS, again, you have 1.6 times 10 to the 7th, 3 times 10 to the 7th. So this would be 3 parts in 10 to the 8th. Okay, so that says Vz is so close to 1, it's only off by a few parts in 10 to the 8th. And for the hard X-ray machines where gamma is more than 10,000, at APS it's almost 12,000, they're even closer to the speed of light. Anyway, so this is a very small quantity, it's true. And this is Vz. And that, but this is what it is if there's no magnetic field, but there's this magnetic field term, which we've discovered through our equations. It's shown here. And it involves, it turns out, it involves, we can, how do I want to say this? I've lost it myself. Oh, yeah. The cosine squared, oh, I'm sorry, this is the half that we get. So I'm confusing myself as to, I know there's a double angle in here, but I don't remember why. If someone sees it, tell me. How do we go from here with the cosine squared of this angle? I think the error is probably this is not a 2, a square. At any rate, allow the fact that I've made a mistake here and I can't find it real time. But this, taking the square root, this is what we get. And this, there's a cosine squared here. And we can replace the cosine squared by a double angle formula. Okay, so we've replaced this using this formula by this. Okay, again, where Ku is defined here to be 2 pi over lambda u. So this is not a wave number. This is just 2 pi over the undulated period. At any rate, this, because this was a cosine squared, we can replace it using a double angle formula. And now it's, this is what we're left with. So Vz has this part, okay? And from this, there's 2 terms. This thing has 2 terms. It has a 1 plus a cosine of the double angle. So when you put that in here, there's a k squared over 2 gamma that comes over here. It's a constant, right? It just depends on k, which, just say for the moment, is fixed. So Vz is not only slowed down, is not only a little less than c because of the gamma squared, but it's slowed down even further by k. So there's a general slowing down, but there's also a double frequency here, has come into this game. And a question is, where is this double frequency coming from? Okay. And by the way, in a moment, we're going to do an average over a cycle, and we're going to lose, this will go out, and this will become the VZ term when averaged over a cycle or over n cycles. And this is where we're going to see where on average there's a slowing down because of K, the magnetic field, and this will give us a new definition of a gamma equivalent. The double frequency, I hope, is in the next figure. It's not. Let me do this first. Let's just average over a cycle. If we average over a full cycle, this term is going to go to 0 because we're averaging over a cosine or a sine function. Average over a full cycle, it goes to 0. And so when we average over a cycle, we'll get an average velocity in the z direction, which is just this term. Okay. So here's our z velocity averaged over one cycle or n cycles. And this is what it looks like. This is just a copy of what was there at the bottom, leaving off the cosine double angle. Okay. So what this is saying is, actually, what we could do is we could introduce an effective Lorentz factor where, if you recall, we had 1 minus 1 over 2 gamma squared. This was extra. So let's define a new gamma, gamma star, that includes all of this stuff. Okay. So we're going to have a gamma star that replaces that. Now, when we write the equation, so this will be VZ over C is equal to 1 minus 1 over 2 gamma star squared. Okay. Having done that, we now go back to the undulator equation, or almost undulator equation we had before, which had the gamma star appearing twice, once because of the Lorentz contraction and once because of the Doppler. But we were aware that those values of gamma were not quite correct. They didn't include the slowing down, but this does. Okay, so we're going to replace the gammas by gamma stars, where this is the gamma star. If we do that, just make the substitutions in both places and carry out the algebra. This is the undulator equation that you get. Okay, so this is the tuning term. So as you close down the magnetic structure and you increase the magnetic field, it takes the electrons longer to get through the magnet structure to do the n oscillations, and as a result, the wavelength is longer. Okay, and this is just some practical formula of that. So going backwards, frankly, I can't follow what I did wrong, what I'm doing, what I've done wrong between this step and this step. But between this step and this step, there's no doubt this is correct. Okay, and maybe one of you can catch me at it, or I'll figure it out later and correct the slide. Okay, so now we have the undulator equation. We have the full undulator equation, which we didn't have before. It is a major achievement. We now know what wavelengths we're going to see on axis. We've explained all of the factors, the 2 gamma squared, the off-axis term, and the magnetic tuning. We basically have everything there is to know about the wavelength on axis and what it is off-axis. And it's a major achievement. The thing that we don't know is what's the photon flux within that cone. And so that's what comes next, I believe. Yeah. So here we go back to our discussion about the electrons coming through this magnet structure, and if we move ourselves to move with the frame of reference, moving with the electron, if we join that frame of reference moving with the electron, it's called a Lorentz transformation to a new set of coordinates, prime coordinates, and in that frame of reference, the electron is simply oscillating up and down. There's no z component of motion. It's not relativistic. It's not relativistic at all, and it's radiating at this shorter wavelength. Not only, so we knew that before, but also, and what this is actually done in the book, this calculation of, okay, what is the power radiated? Actually, we don't even need to do this. Back in chapter 2, when we were looking at scattering, we wanted to calculate the power per unit solid angle. We weren't in some strange reference frame moving with the electron. We just wanted to know if an electric field makes an electron oscillate, what is the power? And we calculated that. So I guess this is going back to chapter 2. This is what we found. We got the donut pattern, this sort of wraparound donut pattern. And where capital theta is measured from the acceleration direction. And we're mostly interested in this little angle close to the z direction, okay? But power is going into all these angles. We want to capture just a part of it. And remember that the power radiated depended on acceleration squared. And we know how to calculate acceleration because we've just calculated in that frame of reference. We've just calculated velocities. We can get the accelerations. And if we do that, this is what this formula with the expanded angles looks like this. And the acceleration has been expanded to include all of these factors. So, you know, radiating as k squared and 1 plus k squared because of the slowing down. So this formula in our frame of reference looks like this, still in the primed frame of reference moving with the electrons. And then we're going to do the inverse Lorentz transformation. We're going to transform back from the frame moving with the electron to the frame of reference in the lab. And when we do that, we just want to transform this algebraic relationship. And when we do it, this expression becomes this expression, where I've done two things. I've averaged over a cycle, so it brought in a factor of a half, amongst other things. And I did it not just for one electron, but a current of many electrons. So if you look in the book, read this part of it, you'll see how the single electron result, which we had here, how that changes, or how you account for the fact that there are many electrons. And we usually do it in terms of a current I. So now we have the undulator equation telling us what the wavelengths are on axis and slightly off axis. How big is this radiation cone? And by the way, we said the radiation cone was 1 over gamma square root of n, but actually now we see that we had to replace gamma by gamma star. So this is a gamma star is a little bit smaller than gamma. And in fact, it'll have a k squared in the numerator here. 1 plus k squared, I think, over 2. And so there's a little change to that, but not a big change, okay? So now we know the wavelengths, we know the cone angles, and in fact, we know the power. One thing we probably want to do, because we're working in a synchrotron community, is to replace power by photon flux, which is a simple thing to do, but anyway, we need to do that, okay? Could I stop here for a question or a comment?
Yeah,
Go ahead.
okay, so I actually had a question regarding the undulator equation.
Yeah.
So with that, we see that as we increase our magnetic field by moving the jaws closer together, we get a longer wavelength. So then as we move them apart, we would get a shorter wavelength. At what point does that separation of the magnetic jaws result in us no longer having an undulator? Like, is there some sort of defined cutoff where we have like a minimum B field, or how do we kind of resolve that?
No, actually, I don't. There may be some practical thing about how far can you move the magnets, but you know, remember that the power radiated depended on k squared. So when you get down, so for instance, it's quite unusual to run k as low as a half or even less than a half. But actually going to 0, I don't know that anybody's ever done that. I'm sure somebody's done it, but generally we just go to where, you know, if you remember the tuning curve we showed, that was sort of cut off, actually. I didn't go all the way to 0 where the curve would have hit the axis, but maybe if you don't, I think, let me just see what's ahead of us. Yeah, so just moved ahead. When k is equal to 0, this thing comes down to here. And so you'd go back into the undulator equation and figure out what was the wavelength or photon energy, but you can see where this is headed. It's going to be less than 500 eV. There's going to be no power coming out whatsoever. You're just not going to get anything. And then as you go up. So typically I plotted these curves for values of k equals a half to something like 2 or 3.
So it's kind of like a balancing act between your output power and your photon energy
Yes.
when you're kind of adjusting it. Okay.
Yeah, exactly, a trade-off, right. Lorena, you were going to say something.
When you were talking about using the extending it to a lot of electrons using a current,
Yeah.
how does that relate to?
Say again.
How does that relate to the fact that the electrons are in bunches? Is that relevant to this current, or because it's? I guess what I'm getting confused about is it's not like those electrons are moving at a constant flux, given that they're in bunches. So how does that relate?
So it turns out that their axial velocities are almost the same within about 1 part in 10 to the fourth. So there's not a big difference in their axial values of gamma, okay? But you've hit on a really important issue, which I haven't said too much about so far, but we're going to say a lot more as we get to the free electron laser. But we're representing a bunch of electrons coming through, and maybe 10 to the eighth or so electrons, and there's no coordinated motion amongst them. It's just complete chaos, random motion, bouncing into each other, etc. And in that case, they each radiate some wave, but because it's all random, there's no phase relationship. The electric fields between any one of those electrons and another electron is averaged over a cycle, likely to be uncorrelated, and therefore the electric fields will not add in phase, so there'll be no special effects. Okay, if the electric fields start adding in some way, interfering positively or negatively, then we're going to see something. And in fact, when we get to the free electron laser, it's going to be a giant effect. But so here we're saying that I took the power radiated by a single electron and multiplied it basically by the total number of electrons in the bunch. And they're all moving at the speed of light almost. So we replace it by a current. Okay, so
Okay.
there was a density of electrons and there was a velocity. You can see where the current comes from. Great,
Okay.
good questions. Yeah.
So we're specifically doing this for one bunch of electrons. That's how you've chosen the current.
Yes, actually we did the calculation for a single electron, and then we said, well, actually, to get the result for 10 to the eighth electrons, we just multiply by how many there were. Okay.
Okay.
But while you've raised the question, just to jump ahead to the FEL, in the FEL, we're going to all of that random collection of 10 to the eighth electrons, all moving around randomly. There's going to be an effect that takes place that causes them to microbunch into little tiny bunches. So within this bunch, which may be a few centimeters long itself, okay, let's just make up a number, centimeter long, we're going to see that they're going to microbunch into what's going to look like an axial wave motion. All of the electrons in the bunch in the FEL are going to be in this nice electron wave that starts at one end and goes to the other. And in that case, the electron motions and oscillations and the radiation wavelengths are all the same. All the electric fields are going to add in phase. And that 10 to the eighth electrons is, radiated intensity goes as E squared. So all of a sudden, that 10 to the eighth factor of how many electrons in the bunch is going to lead to an increase in power. It's going to go from just, in the undulating random case, capital N, the number of electrons in the bunch, it's going to go to N squared. And that's going to get us an extra factor N, which is around 10 to the eighth. So we're going to go from watts of power, a watt of power at the ALS, or 10 or 12 watts of power at APS, multiply that by 10 to the eighth. And the FEL is going to get gigawatts of power, okay? And it's going to be coherent. So that's where we're going.
Got it.
Yeah.
Cool.
Does anyone else, does that raise a question for anyone they want to pick up on? Okay, I don't know where I was going to put this in, but this is just about if our electrons or electrons go through this magnet structure and they radiate, they oscillate N cycles because there's n periodic cycles in the magnet structure, they're going to radiate a wave train which has n cycles. This might be what the electric field would look like. And if one does a Fourier analysis of this to find out what is the central frequency, that we'll get from here, right? Okay, so that'll give us a central frequency when we do a Fourier transform, but it has a little bit of a width because there's a lack of definition, there's an uncertainty by the number of cycles. So if you if you have 100 cycles, you get a certain width. If you have 1,000 cycles, the definition of the wave fronts, where the peaks are, is less affected by the end effects. Basically, the Fourier transform of this into time would tell us that indeed there is a central frequency, which is this, but there is a bandwidth. We'll find it's roughly 1 over n. So I've said this to you a couple of times during the class, but this is a slide that captures it. And so we'll use this all the time. Yeah. So if we have an undulator with 200 periods, then there's going to be a bandwidth, a relative spectral bandwidth of roughly 1 over 200. So does that sit well with everybody? Okay. So this is our summary. We've seen this already before. It has our equations. This is a tuning curve again. It starts with k equals 0, and as you close down the gap, you start increasing k. The magnetic field that the electron feels on axis is going up. The power is increasing as k squared. It's going up until it gets, when it starts to k starts to get around 1, this is no longer negligible. When k is a half, this just doesn't matter, okay? But when k gets to be around 1, this term is 1 plus a half squared, so it's a factor of 2. It's starting to matter. And in fact, when this k gets up to the square root of 2, you've reached a peak. You could just find that out by doing a derivative with regard to k and set it equal to 0 to figure out a maximum or a minimum. This is what you'll find, okay? Okay, and so this has to do with the slowing down, okay? This slowing down, the going from gamma to gamma star. And we'll see in a moment, we also generate harmonics. I didn't quite show it to you there before, but you did see a double frequency. You saw that the electron was not only slowed down as it went through the magnet structure, but there was also a double frequency. Now maybe I should go back to the equation. Here, the VZ, not time average, so now it's got everything there. There is a slowing down term, okay? But there's also a double frequency in the axial direction. This is VZ. So this is saying that VZ is moving along, slowed down somewhat, but then there's sort of like a sloshing back and forth axially. So the electron is going through almost the speed of light, a little bit less, but on top of that, there's a little oscillation at a double frequency. Double frequency is a harmonic. And we're going to see that if we follow through these analyses, we'll find that there's not only double frequencies, there's triple frequencies, quadruples. We're going to do that. I don't know if we'll get to it today, but we're going to do it. So, okay. So this is just a summary of what the different terms are. We did not derive this JJ squared term. I just basically stuck it in there. But this accounts for energy transfer from the fundamental to higher frequencies, driven by axial oscillations. So this is the acceleration squared, which is driving the power. This is the slowing down, and this is an energy transfer. It's not a big effect, actually. Even for k, there's a table in the book, but even for values of k around 1 or square root of, let's say 1, I think JJ squared is something like 0.85 or something like that. So it's a percentage correction. When you're working in the lab, actually, percentage corrections for power radiated will be the least of your problems. Okay, oh yeah, and time structure. So I wanted to mention this to you. I guess I told you before that as the electrons go around the ring, the electrons radiate, and it's somewhat statistical. Not all of the electrons are radiating the same amount, and that, as I described it, you would have thought that, but there's some statistical variation to it. And hold on. at any rate, some electrons are radiating more than others as they go around the ring. And so as a result, they've lost energy and they're a little bit slower. Remember that I said the energy spread, or the variation in gamma, delta gamma over gamma, is something like 10 to the minus 4. So it's not a big effect, but some of them are slowed down. So they put an RF cavity at 500 megahertz. It's in one of the straight sections, and it has an axial electric field. It's oscillating at 500 megahertz. And the way it's phased is that if an electron is coming through and it has not lost any energy, then it comes through when the electric field is 0. It's oscillating back and forth. The electrons which come through not having lost energy don't get any acceleration. But the ones that come through a little bit late, they feel an axial electric field and they get pushed. And it's just the amplitude of that axial electric field. It's in a big, you could call it a microwave cavity, but it's at 500 megahertz, so it's kind of a long wavelength. I don't know if it's 10 centimeters or 30 centimeters, but anyway, there's an axial cavity there, and it's accelerating the electrons that are slow, and it's oscillating at 500 megahertz, and at 500 megahertz, the peak-to-peak separation is 2 nanoseconds. So that RF cavity winds up introducing a modulation of the electron bunch. So even if you sent in an electron, not a bunch, if you sent in a lot of electrons, just in a long, long tail of electrons, this RF cavity would push some forward and some back, and it would form these very nice pulses. So again, at 500 megahertz, it's every 2 nanoseconds. The result is that the electrons going through the ring are in bunches that are separated by 2 nanoseconds, and they have some typical width. It says here 35 picoseconds, but for instance, the ALS can operate at that value, but typically now they operate, I think, at 70 or even 100 picoseconds. And Argonne, the hard X-ray facility outside Chicago, also of order 100 picoseconds, okay? So that's the time structure now, is that every 2 nanoseconds, a pulse comes through your undulator or your bending magnet and radiates for, say, 100 picoseconds, and then it goes away and the next one comes by. Every 2 nanoseconds, another pulse comes through. And for most people, they don't even know that. That's okay. There's a few chemists who use it for timing purposes to look at molecular dynamics. Okay, but anyway, that's how the time structure appears. Okay, at the ALS. Yeah.
It seems like this has two effects. It like replenishes the lost energy to make sure all the electrons have the same energy. Yes. And it produces the time structure, the bunching, right?
Exactly. It has both effects.
And it might be just sort of semantics or not important, but just out of curiosity, is it like we want to make sure they have the same energy and the time structure is just sort of an accidental result of that? Or do we like really want both of those effects? Like, is one just kind of a side effect, or?
I'm not 100% sure, but I would say that the time structure is a side effect. What really matters to us is we want all of the electrons in the bunch to have the same gamma. So we don't have some radiating at one X-ray wavelength and the others radiating at slightly different. Okay? So we want to work hard. They work hard to keep the spread of gamma, delta gamma, to keep that very small. That's the primary driver. With it, you get the pulse structure. And I'm not sure what... I'm not sure what else goes into that decision making, but all the synchrotrons in the world use it, and I think they all use 500 megahertz, whether they are soft or hard X-ray facilities. Okay, so those were a couple of just features that I hadn't told you about. I wanted to tell you about. Now for comments about the harmonic structure. So let's start with this one on the right for just the first and second harmonics. Okay, here's the electron. An electron is coming through along the z-axis. This is one magnet period, by the way, the dashed line from here from the origin to the dashed line. This is a single period, and this is what V sub x looks like. It's going through one cycle like this, okay? So, well, that's the motion. I'm sorry, that's the amplitude. In terms of Vx, one cycle for Vx looks like this. So that came, remember we saw in our equation that well, I'm sorry, one oscillation, one period of the undulator gives us one cycle for V sub x. That's what's shown here. And it has an amplitude of kc over gamma. Okay, so we saw that in the equation before. But so this is what we calculated for V sub x. You know, we had just a cosine or a sine function. But if you notice, in one cycle for V sub x, what happens to V sub z? It actually goes through a double cycle. So we saw that in the mathematics, but you can see it here. Whenever the velocity in the x direction is 0, that means the velocity in z is a maximum. So here, here, and here, Vx is 0. That means at those 3 points in one cycle, Vz has to be a maximum. So here it is, a maximum, a maximum, a maximum. And where Vx is large, whether positive or negative, everything gets squared for energy. This point and this point are going to be ones where the absolute value of x velocity in the x direction is large, and therefore Vz must be small. So at this point, you have a minimum, and at this point where Vx rather is also large, you get a negative. So this is a graphical view of that formula we saw before, which is saying that in one magnet period, V sub x goes through one period, Vz goes through 2. So this is where I was telling you the electrons, where is all this light coming from? As the electron is going through, it's slowed down by the magnetic field, just slightly below C, a little further, but it's double frequency on axis, okay? So this is a double frequency in the Vz direction. So what's happening? It says that as the electrons come through, in the frame of reference moving with the electron, it's doing this figure 8 motion, okay? It has some velocity in the z direction, but it has this velocity in the x direction. And there are two things happening. There is the dipole radiation that we calculated before, okay? So this is in the transverse direction, but in the opposite, in the orthogonal direction, there's a double frequency. So this is an oscillation in the x direction, and it's producing a radiation cone which wraps around the axis. It's a dipole, I mean, it's a donut pattern, but it's a donut pattern where part of it goes in the forward direction. This orange curve here, okay, is our central radiation cone. But the double frequency in the z direction, that's an oscillation in the axial direction. Its donut is wrapped around the axis. This motion in the z direction, double frequency, this is the acceleration direction for that double frequency. It's producing a wraparound donut pattern. And when you relativistically transform that to the laboratory frame, the donut gets pushed down, but there's no axial component. For that z direction acceleration, remember, there is no radiation along the axis for a donut that's wrapped this way. So it comes around to, it looks like a hollow cone. I haven't shown it properly, but the fundamental, which we were calculating, we'll call that lowercase n equals 1, is the frequency, and the double frequency we saw here is a wraparound cone. So there's actually a double frequency there. It's a 0 on axis, and so you have to go off axis to look for it. And most people don't look for it. We just look for a smaller angle than this, actually, for the undulator. We won't even see it, okay? The only way you would see it was if some of the electrons in your ring, in your bunch, weren't all going exactly parallel to the axis. If they're slightly off, then their donut pattern will be off, and this green dashed line hollow cone would be tilted a little bit. So you could see it in an old machine. In the new machines, you don't see it. So this has shown us about the fundamental. That's what we calculated before. A double frequency, which we're not likely to see, but this will introduce even more harmonics. And for some people, they become quite important. So for instance, I'll just show you these pictures on the left here. This is the n equals, this is a simple calculation for a very tiny electron beam. It's essentially small. It was done by, the calculation was done by Kwang Jae Kim, who's at Argonne and the University of Chicago now. But anyway, this is the fundamental, this is for k equals 1. You have the fundamental, and here's a third harmonic. Second harmonic not showing. There's a third and there's a fifth, etc. When you go to even bigger values of k, you can still use this formula for the fundamental, but when k gets bigger, lambda gets longer, the photon energy, this peak is now coming over here. It's reducing. Remember, it's k squared, but it had that 1 over 1 plus k squared squared. So the fundamental is actually losing power or brightness, and it's shifting to lower photon energies. And other harmonics are starting to appear, and they appear very rapidly. It's a high power of k as to how many harmonics you're going to see. This is showing k equals 4. It's almost a continuum, okay? In fact, here's a calculation for the synchrotron in Trieste, Italy, Elettra, 2 GeV, so quite similar to the ALS. And this is, the harmonics are so numerous for k equals 3.7 that at a certain point they're starting to merge, and it's starting to look like a bending magnet. So what do I want to tell you here? This is what we calculated a moment ago for the VZ. It had the slowing down and it had the double frequency. And if you move, so now we have a double frequency in the Z direction. So when we calculate, what is that going to do to the electron motion? We have a magnetic field in the Y direction, and we have a double frequency in the Z direction. What is that going to do? It's going to produce a different frequency, actually a triple frequency. The first frequency component comes from the magnetic field. Let's call that omega. And then there's a double frequency 2 omega. We're going to get a 3 omega term because of this second harmonic in the Z direction. And if we just follow through this, I think it's easier if you read it in the book. We're going to find that there is another oscillation in the transverse direction, same as our first n equals 1 calculation for x. This is what we had before. We're going to find out that there's a 3 omega term. So let's start it again. The VZ with the magnetic field produced a VX. The VX took energy away and produced a double frequency in Z. And now that double frequency in Z crossed with the magnetic field gives us another one in the X direction, but it's a triple frequency. And the triple frequency will mix again with the magnetic field, and we'll get a quadruple frequency like the hollow cone, but it's also going to be a hollow cone. And so we're going to find that there are these many harmonics start to appear. The odd harmonics all appearing on axis, the even harmonics not showing up because there's 0 on axis, but they would be there off axis, okay? And in general, we'll find that the power in these cones, the power in these different harmonics here, you notice they're increasing here and then they fall off. And in general, if you're interested in this, just read that section in the book, but the power in the central cone for some harmonic n goes as k to the 2n. So if k is getting up above 1, even 1.5 or 2, this is a really strong component for different harmonics, okay? So the harmonics grow very rapidly for k greater than 1. I think this is probably a good time. Yeah, these are here for a different reason. Let me say, if you are interested, so this is calculating harmonic power. it's a complicated business. Some people are really interested. If you're doing your thesis that involves third harmonic, you might want to understand this. You can maybe even make a chapter in your thesis out of it. But for us, I would say read it, see if it interests you. If not, no problem. We're not going to have a homework on it. But this is telling you what's the power in the central cone for different harmonics. And this is how it all scales. And this is accurate for the power radiated. But just to show you what did this result in, this is a power at an ALS undulator. This is one with 89 periods. So it's meant to get into the, around 500 EV region. This is its tuning curve. So K equals 0, where this line comes down to 0. You go up K squared, you peak. This is the fundamental we call N equals 1. The third harmonic has the same polarization. The electrons are also oscillating horizontally, and you get this broad third harmonic, and it has a narrower spectrum. The spectrum for the third harmonic is not 1 over n, but 1 over 3n. So why is that? I think the easiest way to see it is in a Fourier analysis. If the electron was going through 100 cycles, we know it's 1 over n. But suppose it's going through 100 cycles, but for some reason, there's some force in the dynamics that's causing the electron to have a Fourier component of frequency, which is oscillating not through n cycles, but through 3n cycles. That's what's happening. There are for the third harmonic, there's going to be 3 electron cycles, maybe not high amplitude, but a frequency component is going to have 3 cycles for every magnet period. And so the spectral width is going to be narrower, 1 over 3, okay? So these are tuning curves for an ALS undulator and for Bessie and for Electra, and they're all quite similar, okay? Yeah, and by the way, all are considering upgrades to go to less elliptical beamline. And these are curves, again, of the fundamental and the third harmonic for ESRF in Grenoble, France, and APS outside Chicago, and Spring 8 south of Osaka. Well, this is something, just in case you're reading the literature, you should do. Our choice, we define theta central as 1 over gamma star square root of n, and it has the advantage that it corresponds to a relative spectral bandwidth of 1 over n. It was a definition. We want to know what angle contained 1 over n. It says other definitions are possible, and generally those angles are smaller by a half. And I give some references here to Kim and Hoffman and some others. I was at a conference maybe 2 years ago where they had a day's worth of speakers talking about different definitions of theta central, mostly just off by a factor of a half. But in fact, if they made the cone smaller, half angle by a factor of half, can you guess what the power was in the cone? So their definition of central cone would have had a reduction in power, let's say by a factor of 4. And the spectral width, not all that different. So I'm satisfied that for what we do, this is a fine definition. And I just wanted you to be aware that on occasion, there are people who write, there's interest in considering other definitions, but they have almost no impact on what you would observe with regard to calculated power, photon flux, or bandwidth. Okay, so something about beam parameters. I need to check. Yeah, so beam parameters and spectral brightness. These are important measures. This is showing a transverse view, a cut through the electron beam. So beam size and beam divergence. The electrons are not all going exactly parallel to the z-axis. They have a little variation around them, hopefully not too much. Okay, so, and the beam size, the beam is considered to be Gaussian in both directions, in the x direction and in the y direction, okay? And accelerator physics people like to use RMS values, sigma values, to describe it. So they'll say that the electron density as a function of x and y is the total number of electrons in the beam divided by basically an elliptical area here, okay, and some Gaussian distribution in the two planes, okay? So that's what we call a beam diameter, a beam size. And I mentioned to you before, but I'll mention it again, the electron beams in most storage rings is highly elliptical. So for the ALS, I think it's 50-to-1 wide. For the harder machines, it's even wider than that, okay? So you might have a small size in the vertical direction, not so small in the horizontal direction. For the ALS, the sigma y is small enough that it doesn't take much spatial filtering to get spatial coherence. The difficulty is you lose about a factor of 50 in the horizontal direction, okay? So this is your beam size. Your beam divergence is accounting for the fact that the electrons are not all parallel to each other. They're colliding with each other. They don't knock each other out of the ring because their effective mass is gamma times the rest mass, so it's quite high. But there is little variations in angle for all the electrons in the bunch, and that's described again by assumed Gaussian. You know, we use Gaussians because they're so convenient. We don't really know that these are Gaussian distributions, but there's something close to that. Okay, so this would be a description. And so sigma x and sigma y are called beam parameters, and sigma x prime and sigma y prime, which are basically angles, are also beam parameters. So they are the four beam parameters characterizing an electron beam. And in the z direction, there's also a length and sigma x, so same thing. One of the things we're going to see is, this is a calculation we did just for this curve, photon flux per unit bandwidth. And what I said was, if you had, what you want to look at is the highest curve here, where sigma prime, that's a divergence measure. Sigma prime over theta central is 0. There is no axial divergence. All the electrons are parallel to the axis. This thing has a width of 1/n. But what happens when you have some electrons coming through which are at a slightly different angle? That slightly different angle is going to produce a slightly different photon energy and wavelength, because when it goes through the magnet structure at a slight angle, the period seems longer. It took the electron going at an angle a little bit longer to get through a period. So it's have a longer wavelength. So you wind up longer wavelengths or lower photon energies. And so this is showing parameterization. When the divergence over the central radiation cone is small, comparable, or large, you increase the spectral width. So basically, if you want to get good undulator performance, you want this parameter to be small. You know, you want sigma prime, the beam divergence, to be small compared to the central radiation cone. For the ALS, that's not a problem. For the hard X-ray machines, they're down in the middle here someplace. And sometimes in the calculations, rather than calculate the radiation per unit solid angle in the central radiation cone, we'll introduce a total angle in the X and Y direction, which combines the central radiation cone plus a measure of the angular divergence. Okay, so we'll use these in a moment. How are we doing on time? Let me at least introduce it. Brightness and spectral brightness. Brightness is power per unit area per unit solid angle. It's a fundamental quantity in optics. In fact, if you have a perfect optic, a lens, which is non-absorbing, and it images radiation from some source into some other plane, the brightness is actually the same in both planes. And what's happening here with this lens is it's demagnifying the source size to something smaller, but in doing so, it's increased the angle. And they're just the opposite they're just the inverse of each other. So brightness is considered a conserved quantity in general. Now, of course, for X-rays, we have absorption, so it's not quite absorbed. It's not quite a conserved quantity, but it's still an extremely useful concept. And so brightness is power per unit area per solid angle. So we've calculated power for our undulator. We know the beam size, the sigma parameters, sigma x and y, so we could make an elliptical area. And the divergence, this could be the power is radiated into the central radiation cone. So we could put the central radiation cone here, or we could make a little correction for the fact that the electrons had a sigma prime, a little divergence to them. So this would be a place where we make this little correction down here, rather than say that it's radiating that power into a central radiation cone and figure its solid angle. We'll make a little correction for the divergence, okay? So anyway, this is brightness, and this is spectral brightness. It's the same thing, but within some spectral bandwidth. So of all the photons radiated in a certain area and solid angle, what part of those photons are within a given spectral bandwidth? So it looked like this. There may be a lot of power radiated, but we're only interested in the part within this narrow band, okay? And we call that spectral brightness. And you'll notice that when the different facilities compare how they're improving, how the ALS is going to the ALS upgrade, they'll of course give you coherent flux and stuff, but they'll also tell you what was the improvement in spectral brightness. And when different facilities compare themselves to others, they'll always use spectral brightness. And so this is what it is. And we can calculate that because we know power radiated in an undulator. We know what the beam parameters are. We can look them up for the ALS, for instance, with the sigma x and sigma y. We can use the central radiation cone solid angle, or we can make a little correction. And we can say that our power was radiated in a 1/n bandwidth, except, and we can do that, and we will do it, but in general, the industry standard amongst all synchrotron facilities and users is to quote brightness in a standard 0.1%, 1 in 1,000, because basically they don't really want to use a 1/n, 1% or 3%. They really want to know how much power they can get in a narrow bandwidth of 1 part in 1,000, maybe even less than that. But anyway, it's the conventional standard. And so we would calculate this power and this spectral power, and that's probably what's here. This is the spectral brightness now. Okay, it's what we had before, but I want to get it in. The standard is not only to do it within 0.1%, but rather than quote it in terms of power, watts or milliwatts. As in the laser field, by the way, this is what we would do. This would be in watts or milliwatts for all of these different things. But in the synchrotron field, the standard is to quote not power, but photons per second, which at a certain wavelength, that works. So that's what's going on in the next slide. We're calculating spectral brightness averaged over one cycle, so we'll use the average power, and we're converting power in the central radiation to photon flux by simply dividing through by the photon energy per photon. And that's going to convert us from watts to photons per second. And if we do that, and we follow through and we use our beam parameters and our solid angle of the central cone, maybe with a correction, and this bandwidth, we are going to naturally radiate in some number of cycles. We don't know for our power, did it come within n equals 55 or an n equals 89? We'll put that in, but what we really want to know is what's the power within 0.1% bandwidth. So it's not obvious that these factors follow as I've written them here, but if you check me, they are. And what you'll find is that the power, the brightness, this spectral brightness that everyone quotes will look just like this. I've just taken the quantities which we know in the book. There are all the details of all these steps, and you'll get an answer which is in photons per second, per millimeter squared, per milliradian squared, and within a 0.1% bandwidth. And if you take one of our undulators at the ALS and put these numbers in, you'll get values which are essentially what the facility would claim. And if you go to Argon or ESRF, all of these numbers work out just fine. So that's probably where we're going to end today. There may be some curves on the next one. Yeah. So here are some curves. This is a kind of graphs that you'll see for spectral brightness. I put in the word average, but in general, people won't say it, but they mean average spectral brightness. It just means averaged over a cycle. And this would be soft X-ray machines like the ALS or Electra or Bessie. And this would be hard X-ray machines like APS or ESRF. These are the undulators up here in brightness units, spectral brightness units. And down here are the bending magnets. You see there are many orders of magnitude. And these numbers are based, this curve I made several years ago, these curves are generally going up as people learn to make their beam sizes, the sigma sigma and the sigma x, sigma y, and the sigma prime smaller. These curves start going up because you're dividing power per unit area per unit solid angle. And the biggest thing that's happening right now is that the facilities all around the world are doing an upgrade, and we'll talk about that a little bit in the next class probably, where they're going to make smaller values of sigma x and sigma y, and they're going to push these curves up. Basically, with the ALS, they're hoping to go up by almost a factor of 100. So their spatial coherence will go up, and their brightness will go up. In fact, by the way, that's a hint. Spectral brightness and coherent power are related. There's a simple relationship between the two, and it's one of the homework problems. I don't know if it's one we'll pick, but there is a homework problem there to show how coherent power is related to spectral brightness, and it's just a lambda squared multiplier. Okay, well, this is just a slide. This is where we'll start next time then. How this is from the ALS. This is by the scientist at the ALS, Christoph Steyer, did this calculation. This is the electron beam now, what it looks like in microns. It's a highly eccentric ellipse, and they're hoping to get so close to a circle, okay? And in fact, if they do, they'll be the only one in the world that actually got so close to a circle. And all of this started at max 4. In fact, I'll tell you a little bit next time about how you reduce this, okay, how you reduce this horizontal spread. Okay, does anyone want to say something before we break? Is it because you're stunned? You've been beaten down, or could you say something?
This might be a simple question, but like, I know that like with beamlines I've used at SSRL or whatever,
Yeah.
the final beam size that like hits my sample is, you know, maybe elliptical, but not like that. So do they just have like, you know, filters or something that they use to make?
No, this is a great. This is really, Lorena, this is a really good question. No, what they're doing, they're using lenses, mirrors, curved mirrors, to take the source, the photons coming from the source and re-image it on the sample. But the optics are not the same magnification in both directions, X and Y. They may be using a so-called a toroidal optic, which at any rate, the magnification isn't the same in both directions. So for instance, often for spectroscopy, they don't care, or they're going to look for scattering in a certain direction. So they want good definition in one direction, but the other direction they don't care about. So different beamline designs can be realized, yeah. So it's a good question. It just had to do with the beamline optics not being axisymmetric. They're a little bit more focusing power in one plane than in the other plane.
But that gets us from this like really stretched out thing.
That's right. It would take that ellipse, it would take the ellipse and bring it into, let's say, a less eccentric ellipse, okay? So spatially it would bring it in, but by the way, the price that they'll pay is the divergence will be larger. So in an optical system, at any rate, that's what would happen. So the divergence would be bigger, in this, if they made it smaller in size, they will certainly make it bigger in divergence. And that might matter for your scattering. Which plane are they doing that in? You know, you might want, for instance, you probably want the incident radiation, I'm guessing, to have a minimal divergence so that you can see scattering to different angles, especially small angles. So probably the bigger dimension will probably be the better one for the angular scattering, because the angular, if it's bigger in area, it's probably smaller in divergence, I'm guessing.
Okay.
You could check. That would be a good thing to just check. Yeah.
And is it still, I'm sure it depends, every beamline I'm sure has different optics, but will it still be like Gaussian in terms of the like intensity as a function of position through the beam stop?
As you say, every beamline is different, number one. And number two, we always assume that things are Gaussian in each direction, but you know, sometimes we clip it with a slit or an aperture or something like that, and so we cut off the tails and stuff like that. Yeah, so different things are possible.
Got it. Thanks.
Sure. Oh, well, we could end on a light note. Okay, this business about everyone has known back here in this slide. It said that the horizontal emittance scales roughly as gamma squared over n cubed, where n is the number of bends. So with the ALS, we certainly, it's 12-sided, so we certainly have 12 bends, but each of the bends is broken up into a couple of smaller bends. But it's been known that we could get smaller emittance if we could go to a higher number of bends. But how could you make it? How could you make them in a way that it was cost effective? And so at Max 4 in Lund, Sweden, led by one Mikael Eriksson, who often leads the international community in really novel approaches. For instance, the top-off mode, where you may be aware of that, where they try to keep the current a constant rather than decreasing every time electrons are lost due to scattering, electron-electron scattering. So Mikael has had several great contributions, and he got the idea of a way to machine the optics so that they would go from 3 bends at each corner to 7 bends. And it goes at some high power. So they really reduced the emittance. And when everyone else saw that they could do it, everyone said, hey, we're going to do that also. Okay. So here's Mikael Eriksson with the king of Sweden, and the prime minister. And I put this in here just to tease my friend. Okay. So with that happy note, we'll see you all on Thursday.